So this is joint work with a colleague from IBM. We actually met last year at BuildSys. We both had a demo paper on metadata, and we decided to work on together since last year. And so Jordan is here, I hope, and myself and one of my students. Okay, so the motivation is actually very similar to the past motivations of the two other presentations. So this morning I woke up at 5 and decided, well, why don't we change that? Why don't we make it a little bit more fun? So I'm going to twist the spiel a little bit and just propose the Beyonce hypothesis. And yes, this is Beyonce, the singer, the female singer. So here we go. The ideal situation is we have an app store in which we find a building application that we want to install in our building, and we deploy it, and it works. But obviously that's not the way it happens. Actually, we are building applications for each one of these buildings separately, which is what the other two speakers have talked about. And this is kind of a dumb way of doing things. So I have a hypothesis. Why is this the case? Well, I think that building automation system users, which are typically facility managers, are very keen on using building automation system points, and they also love Beyonce. And why is that? Well, because if you really like building automation points, because if you, I was going to sing it, but I'm going to try. So if you like it, you should put a tag on it. So if you like it, you should put a tag on it. That's what I think this happens. You know, they're just like very, very carefully tagging things, and they think that's a solution. You know, they follow what Beyonce says they should do, and that's what they're doing. And this is becoming a big problem, right? What we have right now is a lot of tags with very little meaning. And we have no common standard schema for naming these tags, and that has become very apparent in the last two talks. We have also very little information to gather from these tags in order to make a good guess of what they are. There's some hope, especially for newer buildings in which we're starting from scratch, and we can generate tags that conform to some standard schema, like for example a project case tag. But for the other buildings, which are the majority, we need to find a way to normalize them. Okay, so that's the twist on the plot. So previous work has focused on, I would say, three things. One is trying to infer whatever metadata you want, but from the tags themselves. So just using text-based mining, which was partly what the other two talks talked about. And I'm just showing here two examples of those types of work. There's also inference from data or measurements. The other two talks actually also included a piece of this, and they were trying to combine. And these are also examples, many of them actually published at BuildSys. And there's also, obviously, the combination of the two. And the last two talks actually fall under this particular way of doing things. This particular talk, the one I'm going to give now, is only using information from measurements and sort of disregarding any information that the tags may contain. And you may ask, if you had all these papers in front of you, why are you doing that? And I don't know what the answer is, other than we wanted to see how much you could do with just using measurements and not using the tags at all. The results aren't beautiful, but they at least tell us how much we could do if we were going to go down that path. Okay, so what exactly is it that we're doing? Well, first of all, we're going to focus only on the sensor type. The last talk also only focused on the sensor type. It seems to be a very useful piece of information. You know, this is whether this is an airflow sensor, is this a VAV box, set point, or whatever. These are the types of sensors, and that's what we're trying to gather. We are going to do gram truthing by manually applying the haystack schema to all of the tags in the buildings that we have. You know, we go through thousands of sensor points, we manually label them, and then we're going to make an assumption. The big assumption here is that the data stream itself from each one of these sensor points is common, or at least has some statistical distribution that is common for the same type of tag. So distribution for tags that are of the same type is similar. That's the big assumption. And because of that, what we're going to do is we're going to extract some features that represent the distribution of the data stream. And the features are pretty simple. They're just mix, min, max, standard deviation, and the quantiles. So for example, I have two graphs up there of two airflow sensors, one in room A and one in room B from our data set. And I'm showing you the features that we're extracting, just a portion of the features here. So the min, max, mean, median, and standard deviation for the two. And we're going to use this as our feature set or a feature vector, and then try to train classifiers to actually make the prediction from the feature set to haystack tags. And I want to point out that you can think about haystack tags in two ways. One, you can try to predict the whole composite label, meaning in this case, for example, equipment, chiller, cooling capacity, all of those at once as one class label. Or you could separate the haystack tag into individual tags and just talk about air and trying to predict whether the tag air is contained within the full tag. So here's a diagram of how the process works. We start with measurements from BAS. We clean them, we extract features, we train classifiers, and then we do the inference and hopefully integrate all that so that they can be provided for BAS applications. All right, so we needed to test this idea somewhere. We used two specific buildings, one in Carnegie Mellon's campus, the Gates Hillman Center, and the other one at Dublin, where Jordan was working. And these two buildings are similar in size, 3 floors for Dub, we're going to call it Dub, and for DHC we have 9 floors. A bunch of different sensor points. The main difference is that for this one we have data collected over 3 years at different resolution, and we only have 1 month, actually we have 2 separate months for the GHC building, collected at 16-minute resolution. All right, so just to give you a feel of what the data looks like, these are all the tags. On the left, you have composite tags. That's a distribution of composite tags. And again, to remind you, composite tags are just the haystack tag completely with all the tags together. And I'm showing the distribution across both data sets, GHC in orange and green Dub. And for individual tags, we have similar distribution. It's almost Pareto distributed, which is useful for the types of applications that we're going to be doing. So the question is, given this set of tags, which are many, many different types of tags, can we build classifiers that, using the features of the data, predict those tags? And there are 2 strategies that we follow. The first strategy is to take the time series, map it to this feature vector that is just statistical features of the time series, and then create a function that's a classifier that either predicts the multi-class problem, meaning the composite label, or predicts individual tags for each of the haystack tags. So one classifier could be a V, one for air, one for flow, and so on and so forth. It just says this tag is there, yes or no. Very important to mention, in all the results that I'm going to be showing next, we use 20% of the data to train, 80% of the data to test, and then we split the data set in a stratified way, repeat it 30 times, and then we just report the average performance. I mentioned this because in the previous 2 talks they were focusing, which I think is a good focus, on how many tags you need to be labeled for you to achieve certain classification. We applied this rule throughout, and we stick to it. There will be additional work to be done if we want to know exactly how many tags to get some performance. And then, in order to report performance, we noticed that just looking at accuracy alone wasn't enough, and you'll see why. So we're reporting, in addition to just the regular confusion matrix, we're also reporting F1 score, which is basically a harmonic mean precision and recall, where it's a normalized version of having all these features except the true negatives. Okay, so how does it look like? If we want to try to predict composite labels, which would be the ideal case, we just train a classifier and it directly tells us the full composite label. The results are not that good. You can see here we have on the x-axis different types of classifiers, just taken from a machine learning library, scikit-learn in this case. And then the performance. And the performance is reported in a few ways. We're showing true positives, true negatives, false positives, and false negatives, as you can see in the color coding. But we're also reporting the F1 score, and that actually tells a better story, or a more realistic story. So the F1 score is about 70% for at least 3 of the classifiers. But that's the best performance we got on that data set. What happens if you change the number of training examples that you're giving the classifier? We'll see that next. Here's the same story if you look at it now focusing on one single classifier and see how well it performed across tags. So that was the average. Now we're seeing across all tags. And you can see again that for a portion of the tags it performs very well. Again, looking at the F1 score, which is the black line. And for some tags it performs really horribly. So these things are not very useful. Since you can't see them very well, I tried highlighting these two. So I'm going to highlight the electric meter electrical system reference on this side. I think that's a blue circle there, which shows the, no, actually, no, I'm wrong. The electrical meter are the two dark blue circles that are encompassing some blue dots. Those blue dots are electrical meters. And what we're looking at here is, since I can't show you the 6-dimensional feature, min, max, mean, and standard deviation, I'm actually just showing an embedding on 2 dimensions. This is the T, S, and E embedding. And because of that, you can see that these are well separated, I mean, at least in this projection. And the same happens with the temperature sensor, which are the magenta dots. So since they are well separated, they show up with high accuracy over here as well. Yes? Right. So we have, let's say, 1,000 possible composite labels, right? And if we predict that specific sensor falls into that specific composite label, then that's a true positive. But there are many other composite labels that are not that one. Those are the true negatives. So that's why I mean, like, it's really important to figure out how to evaluate this, because true negatives are going to be very high because of the number of possibilities you actually have. So I asked earlier what happens if you change the ratio of data. So we started with 20%, as I said before, but if I increase the training ratio up to 90%, results don't change that much. So even if I trained on 90% of the data and tested on 10%, on both data sets, it remains the same, which is kind of interesting. Okay, so the takeaway from that part is that no matter how much we train, if we try to predict the full composite label, it's going to be really hard. So then we said, okay, so let's try it on individual tags. Instead of trying to predict the full composite label, let's just detect whether it's a sensor, whether it's air, whether it's a VAV, and so on and so forth. Which seems unintuitive or maybe impossible, but for some sensors it actually works really well. So in GHC, there were some tags that had more than 90% F1 score. Those were tags like cool, hot, water, temp, heat wheel, valve. Those achieved 90% F1 score. And tags with high false positive, false negative, which would be the bad ones, are things like sensor, air, and valve. And obviously sensor is a really good example of that. There are a lot of things that can be censored. Right? In dub, we have 30% of the tags have more than 80% F1 score. And some of the tags that are not very good are things like FCU ref and FCU. And I'm showing the results there. You can see the 80% and the 90% that I talked about just as a reference. So okay, so that seems a little bit promising. Why don't we take that idea and then combine all of those binary classifiers to try to predict the composite label? Right, so we have classifiers that can predict individual parts of the tag, and we combine them and use them to predict the composite label. There are two strategies that we use. The first one is a naive strategy, which says, well, if the classifier predicted that this was the class, I'm going to include it in the composite tag, regardless of whether it makes sense or not. So we take every output from each one of the binary classifiers, and if it's a 1, we put it in the final tag. So you can see why that's naive, because some of the possibilities that you come up with are not present in the ground truth. So there could be sensors that are impossible to have in the real world. So then we decrease the number of possible outputs by constraining that set to just a set that we saw in the ground truth, which seems like a logical extension. And actually the results are not that different. At the top, I'm showing the unconstrained case, and at the bottom, I'm showing the constrained case. And you can see that actually the distribution doesn't change that much of the results. So these are the composite labels that were predicted. The take-home message here is, again, for a few things this works very well. For most things, it doesn't work very well. So the question becomes, when do we actually use this, and when does it make sense to use it? don't know if I have any zoom-in version of this right now. No. Okay, so a couple more tests before I finish. We tried training and testing across seasons. Why is this important in this case? Well, since we're looking at statistical distributions, some of these sensors have different statistical distributions across different seasons, right? You can think that temperature during the winter months is going to be different than temperature during the summer months, let's say. And surprisingly, some of these things showed relative insensitivity to seasonality, things that I would think should have been sensitive to seasons. So for example, outside, which is just a tag, it could be outside temperature, it could be outside position, showed 80% F1 score if you train it on December and test it in June, or if you train it on June and test it in December, about 80%. That's good F1 score for outside. And similar results for other types of tags. A lot more investigation needs to be done for making any conclusive arguments about this, though. We also tried training and testing on different buildings, but the results were so poor, I would say, that we didn't even want to show them here. They just are unconclusive. We don't think that was necessarily a generalizable result, so we didn't want to show it. But yes, they were pretty poor when we tried to test on one of the buildings and training on another one. What else should I say about this? Well, I have 3 minutes left. I'll acknowledge that my student was supported by the CSE in China, and obviously thank to FMS at CMU and to IBM for providing the data set.